Oh, it's recording. Yeah. Okay, good. Yes. Okay. So, yeah, let's recall where we arrived at in the last. Oh, yeah, this one. In the last lecture, and then we'll continue because I think last lecture I went a bit fast over some stuff, so I want to just go back and take another look. Okay, so that's better. Yeah. So, yeah. So, yeah, last lecture. So we arrived at a kind of new representation for zeta function that was it's called Riemann's integral representation. Of zeta. So the formula, the presentation was this: 2i sine of pi s gamma of s zeta of s is equal to integral from infinity to plus infinity minus x to the power s over e to the x minus 1 dx over x. So, I mean, one of the consequences of this, of course, was that since right-hand side is actually a holomorphic function in S everywhere, looking at zeros of sine pi for S negative and poles of gamma at S negative integers, they cancel each other. So it follows that left-hand side actually is holomorphic everywhere, I mean, except for zeta, and is non-zero. Right-hand side is, I mean, at least for S negative, right-hand side is holomorphic everywhere. So it means that zeta can be defined for S negative as well. So let me write the argument and that's, okay, so right-hand side is holomorphic for all S belonging to C. So this you know the argument for that, right? Because this is a almost polynomial growth. Well, I mean, this is exponential decay at infinity. And by the way, here, what is this? This means really Riemann's notation for integration. So you come along, you pass through, you don't pass through zero, you just bypass. And here you should not be too high. I mean, for example, 2 pi I and 3 pi I are above, but so you should be below 2 pi I. So you should not cross that, and below also negative 2 pi I, and so on. I will discuss the relevance of these pi i's later on. So this should be your domain, and that's what that's how Riemann writes. And okay, now right-hand side is holomorphic for all. Left-hand side is, I mean, so not left-hand side, I should say in the left-hand side, 2i sine of pi s gamma of s is holomorphic and different from zero for all real part of s less than zero. Okay, so what's going on here? So the idea holomorphic. The idea is that look at where are the poles of gamma at real part of S negative? They are at negative integers, right? The poles are at negative integers. And at those negative integers, exactly sine of pi s has zeros of order 1. You know that. So they cancel each other. And gamma is never 0, we know. And sine of pi is never 0 except at those zeros that we know. So it means that this factor is holomorphic and different from 0 for real part of S less than 0. You see? So what does it mean? It means that if you divide, it means that zeta is actually holomorphic also for real part of S less than 0. That was his argument, his second argument for holomorphic continuity. So corollary is that zeta of S is holomorphic in, zeta of S, I should say it can be continued analytically for real part of S less than 0. So let me write it in a better way. Zeta of S can be continued analytically to real part of S less than 0. Because you can say, originally this formula, you derive it for real part of S bigger than 1. But we know that zeta, anyhow, it is holomorphic for real part of S bigger than 0. So for less than 0, this argument shows that zeta can be analytically continued to real part of S less than 0. Now, what happens on real part of S equal to 0, that also follows from this formula, but I don't want to get into that. But that really follows from this. So there are these arguments that are all based on this. Okay, and this was Riemann's first proof of analytic continuation of zeta. Zeta S to S belonging to all points in the complex numbers except 1. Right? Except 1. Now, it may be any questions? Yes.
Somehow have existed data or part.
Yes, yes.
And somehow.
Yeah, exactly. Yeah. Okay, you're right. Definitely this shows at least that the function can be analytically continued to real part of S negative. Yeah, there's a formula. Whether this formula is useful or not for actual calculations is another matter. Because there is another formula which is called Riemann-Siegel formula, which was discovered much later. But he had it already 70 years before it was discovered. He never published it. But I'll tell you a little more about that. But for calculations, maybe this is not the best formula, but it certainly gives us something. I will mention. Any other questions? Yes. Yeah, it's certainly, but yeah, you can read it in Edwards' book. He has a fantastic book called Riemann's Zeta Function. He really cleaned a lot of statements in Riemann's paper, make it accessible, and also what happened after that up to maybe 1930s, 1940s. Yeah. Yeah, it's called Riemann's Zeta Function.
Oh.
I highly recommend it. I mentioned it actually. But you can read this in almost any a good book in analytic number theory, Riemann zeta function. You can read it in Patterson's book or Titmar's book or this one. Any other questions? Yeah. So again, about the proof. So let me write down idea of the proof again. This is also recalled, but I went too fast in last lecture, so it might be a good idea to look at the proof again. So what is the starting point? Of course, the starting point is the formula, you know, lambda to the power minus s equal to, what is the formula? 1 over gamma of s, right? Integral from 0 to infinity e to the minus lambda t to the s over t dt, right? For both proofs, this is always like the starting step. And then you replace lambda by n. Then you get n to the minus s is equal to 1 over gamma of s, integral from 0 to infinity, e to the minus nt, right? And then t to the s over t dt. And then you sum over all n. So this is for n equal to 1, 2, 3, so on. You sum over all n's, and on the left-hand side, you get zeta function. Let's see what you get on the right-hand side. Sum over n. You get zeta of s, which is by definition 1 over n to the s. And from 1 to infinity, that's equal to integral 0 to infinity sum e to the minus nt, and from 1 to infinity, t to the s over t dt, right? So, and then at this stage, I said that there are two roads, maybe more, I don't know, but there are at least two roads, and he took two roads. He invented these two roads, actually. He saw two roads. One was to turn this into a theta function. That was the proof that I gave first. Is actually his second proof. And another one is you just don't try to be creative with this. Just sum it as geometric series. Just sum as geometric series. You get 0 to infinity. Well, if you sum this as a geometric series, what do you get? You get e to the minus t over 1 minus e to the minus t to the s over t dt. What you can write is certainly as 0 to infinity. If you multiply by e to the t, you get t to the s over e to the t minus 1 dt over t, right? We just do that. Now, so this is now almost like the right-hand side, but it's not quite the right-hand side. I mean, the reason is that the domain of integration here is from 0, is on the real line. This is just a simple, usual real variable integration. You are over the real line up to plus infinity. What he does is that, and this is a common technique in complex analysis, you just perturb the domain, the contour of integration, a little bit above, a little bit below. So you just choose this. And now you have to see a relation between this integration, this one, and this term here, first of all. You're not going to say this is equal to that. Definitely not, because this is zeta. This is zeta multiplied by these three other factors. Yes? Oh, yeah, 1 over gamma I missed. Yes, exactly. And that's the gamma that goes to the left, indeed, yes. Good, yeah. Yes, it should be indeed, yeah. All right, so now we want to relate this integral to that integral, because gamma has been multiplied and is gone to the left. And the reason, so first of all, I mean, yeah, what does this mean even? minus x to the s. What's the meaning of this term? Because s is a complex number in general for real part of s bigger than 1 for now. So this is all for real part of s bigger than 1 for now, because left-hand side is only defined for real part of s bigger than 1. And what does it, so s is complex number, x is also a complex number because you're in the complex plane. You're just moving like that. No? What is the meaning of that? Well, I told you that this is, Riemann takes the following definition. So this is e to the power minus s. Okay, so s log of minus x, right? This makes sense because e to the log of something is that minus x, and this is s. So now the question is, what is log? Log is a very difficult object, but we have to choose a branch of log. But here we don't have log of minus x, right? So for this, you want a function that's defined everywhere on the contour. You want it to be defined on the contour, right? So to do that, you just choose the branch of log that misses the negative real axis. Because if you're here, let me write it. Yeah, choose the branch of log. So we delete this half line, right? And then the angle that you're choosing here, the angle also, I mean, first of all, you cut a half line, and then you have to fix the angle. Angle goes from minus pi to pi, not 0 to 2 pi. It's important. The angle here is near negative pi, here is plus pi. That's the angle we choose. So as you go on, you just... Now, with this definition, then you see that as you move up here, the argument of this log minus x is very close to minus pi. And when you are here, because minus x moves here, its argument is very close to pi. So then, so let me write this integral now. Integral from plus infinity to plus infinity minus x to the s over e to the x minus 1 dx over x is equal to, as I said before, I mean, in the last lecture, we divided into 3 pieces. First of all, you come here up to delta, and then you just go around almost like a circle, and then you continue. So this is just symbolically, I just write integral plus infinity to delta plus integral from delta to minus delta, I suppose. No, so absolute value of x equal to delta. I mean, so by this, I really mean this part, not the whole thing, only part of it. But remember, this thing is approaching to 0. We are pushing down at the same time, but anyhow, so plus integral from delta to plus infinity. The integrand is the same. Okay. So then we argued that, and that's not difficult, that this part actually goes to 0. Now, on this line, something very interesting happens. As you push down this line to the axis, what happens to log minus x, for example? Because here we have got, okay, so we have this definition here. So we have minus x to the power here, s Okay, so to the power s, which is e to the, so let me just write log minus x. So, so let me write it like minus z to the power s approaches to log of x plus I pi. Right, minus I pi. Minus I pi. On the upper branch, upper contour, where z is right x plus iy. Because as you push down, so here is z, which is like x plus iy. You're pushing down, so you're approaching to the real part of this. And what is log, by the way? Log is just log of the absolute, the real part is log of the absolute value of the thing plus the argument, I times the argument. So the argument is minus pi. You're here, right? So you're approaching this part, the argument goes to minus pi. So this is the part. And in the lower part, so let me write it here. In the lower contour, minus z to the power s is converging to log x plus I pi. Because when you are here, when you do minus x, you are in this part of the log. So you pick up the I, you're very close to I pi. So that's a very delicate argument. I mean, you have to sit down and think a lot, I mean, about it, but you see that it's very judiciously, I should say, chosen. It's really amazing choice of contour on his part. Question? So the formula now, so this basically approaches, so let me write the formula now. And that's the formula that we had last time, but I want to, so this whole thing approaches to integral from yes, so we have to take this limit as delta goes to 0 of yeah, yes, delta to infinity. Yeah, this is negative, definitely. So let me write it like this. Integral from plus infinity to delta on the upper part. You get exponential of s times log x minus I pi over e to the x minus 1 dx over x plus integral from delta to infinity exponential of s log x plus I pi over over e to the x minus 1 dx over x. Yeah. Now here, as you push down, eventually, so delta goes to 0. So this approaches to the limit is actually equal to e to the I pi s minus e to the minus I pi s. I hope I'm not off by a factor of 2, but this is integral from 0 to infinity, x to the s over e to the x minus 1 dx over x. I mean, this, yeah, my notation is not ideal. I mean, there are some little bit of fudge involved in my notation because I'm choosing x before approaching the limit for the value of the limit value of x, because I should really put here z instead of x. But in the limit, this z approaches a point on the real line, so it becomes x. I hope that's clear. And so what about this part, e to the I pi s minus e to the minus I pi s? What about that part? Can you tell me where this factor comes from? Yeah, this phase gets out because, I mean, there is no, it only depends on s. There is no x involved here. So it comes out of because of linearity of integration, it comes out. And here also comes out, and you have this factor e to the I pi s from here and e to the minus I pi s from over there. And there's no two involved. And of course, this is related to sine function. So yeah, we get everything. And there is some, yeah. So yeah, well, what is the formula that we use here? Sine of z equal to, can you tell me expression of sine in terms of complex exponentials? E to the iz minus e to the minus iz over 2I. This sounds right, but okay, so how can I check this now? Euler's formula? Which formula? Euler has zillions of formulas.
Right into the sine code.
E to the I, so you just e to the I theta equal to cos theta plus I sine theta. I know that this is true for theta real, but now I extend it to theta complex because both sides are holomorphic functions in theta. So if this is true over reals, then it's true everywhere. And then, yeah, okay, I believe that. Yeah, you're right. Yeah. Okay, so everything really comes out of this observation that, I mean, this contour here. So this I went very fast last lecture, so I wanted to. Any questions? Yes. Yes. Oh, that approaches to 0. What was my argument for that? Yeah. Yeah, I think that was the idea. But what shrinks to 0? The length of the circle shrinks to 0. That contributes. But then what else was it? You mean this function? Yeah. I'm not quite fresh on that. Actually, I have to write it down in detail. But yeah, this is what happened. Yeah. Maybe over the break we'll think about it. Yeah, I just don't quite see it right now. Yeah. Okay, so yeah, I mean, this is amazing argument. I mean, because again, I mean, the right-hand side is defined for all S complex. So that's the proof of analytic continuation, but it's not a proof of functional equation because that's another issue. So let me write. Can I erase this now? Yeah. Okay. So maybe I start from here erasing and then. Okay. So proof of functional equation remember functional equation was z of s equal to z of 1 minus s, where z of s by definition was pi to the power minus s over 2, gamma of s over 2, zeta of s needs more work. I don't know if I claimed in the last lecture that actually now we have the functional equation as well or not, but when I thought about it, we don't have the proof yet. It needs more work. And in fact, you have to choose another contour using this method. So have to choose a new contour that contains complex roots of e to the x minus 1. So what are the complex roots of e to the x minus 1? So e to the x minus 1 equal to 0 if and only if x is equal to, what is the answer? What are the roots of e to the x equal to 1? 0 is 1. What else? Huh? What? Multiples of 2 pi? Well, e to the 2 pi is big number. It's not 0. I to pi, you meant. Yeah. This is one of the also Euler's formulas or whatever. X equal to 2 pi n I. N belongs to Z. So now you have to consider so this is what I alluded to at the beginning of the argument. This is 2 pi I, 4 pi I, negative 2 pi I, negative 4 pi I, and so on. So what he does, he chooses a contour that goes through like this. Yeah, it goes to infinity and comes back. And so by looking at contributions of residue, because the function has residues at all those points, right? And by considering the contributions of these residues, he proves the functional equation. It's again kind of long argument. I don't want to give it because we have seen one proof of analytic, one proof of functional equation. Anyhow, and but it's worth looking at Edwards or some other sources of this proof of functional equation. What I will do is I use some similar ideas to actually compute zeta at even integers, or to derive Euler's formula using this. Okay, so today we use this integral representation to compute zeta of 2n for all values of n, for n equal to 1, 2, 3. So you remember I calculated this using a method which is not totally beyond scrutiny. The method I used gave us the values of zeta 2 and zeta 4. And I said that Euler used that method to compute first up to zeta of 16 or zeta of 14, something like that. But now we are going to use a method that computes all of them at one go. But again, this is quite involved. So let's recall Bernoulli numbers first. I mean, this is one of the most important sequences of numbers in mathematics. Yeah, Bernoulli numbers. I mean, it's just they appear in so many places that, I mean, together with Catalan numbers, they're really just the two most illustrious families, sequences of numbers. So there are two conventions, unfortunately, for Bernoulli numbers. If you check Wikipedia, it gives you two conventions. So the one that I'm using is the following. You just expand this function, sigma bn x to the n over n factorial, and from 0 up to infinity. I mean, this function is holomorphic, x over e to the x minus 1 is holomorphic here in this disk of radius 2 pi at the origin. So there is a power series expansion there. Okay, so there's a power series expansion. You expand it, and there comes these numbers bn. So you can say x over e to the x minus 1 is the generating series, exponential generating series of bn's. So then you can compute some of these things, at least by hand. You can see that b0 is equal to 1, b1 is equal to minus 1/2. Then b2 equal to 1 over 6. b4 is equal to negative 1 over 30, I believe. And b6 is equal to 1 over 42. So it takes a lot of work to compute these things beyond b2, really. But you can also show that b2n plus 1, the odd ones are all 0 beyond 1. So for all n bigger than or equal to 1. I invite you to prove this because that's a kind of interesting problem. Question? So these are Bernoulli numbers. Okay. Now, and so, yeah, you see that these Bernoulli numbers, I mean, this generating function, it actually almost appears in the expansion, in the integral representation for zeta. This is the right-hand side. There is 1 over e to the x minus 1. You have it there, right? So, yeah, in fact, you're going to use this. So let's compute then. So let n equal to, so I mean, s equal to minus 1 and big N equal to 1 in the integral representation. Integral formula. And then you get zeta of minus n is equal to gamma of n plus 1 divided by 2 pi I integral from plus infinity to plus infinity minus x to the power negative n divided by e to the x minus 1 dx over x. Now, something interesting happens here. Since this power is an integer, this can be computed in a different way. This time now, this guy, we don't need log for this because n is an integer, right? So you can directly write this to this power and divide, and then you integrate. So I'll tell you what happens. This case. So what happens is that this actually becomes equal to, so let me continue here. This is equal to, well, gamma of n plus 1. What is gamma of n plus 1? I'm not going to bet any money on that. But what? Well, that doesn't help me. What is gamma of n plus 1? That's not good. It's a 50-50 chance on mathematics. No, what is it? I'm glad I asked because I was going to assume, you know, huh? No, it's n factorial. Gamma of s, guys, I told you several times, gamma of s is s minus 1 factorial. This is the philosophy of gamma. Gamma of s is s minus 1 factorial. Okay, so this is then n factorial. So n factorial divided by 2 pi I. And the integral comes to be just over the circle. Some small circle. Sum, you just write it, sum bm over n factorial. Bm over n factorial. Sum over m. And here is xm. Here is minus x to the power n over x, dx over x. I mean, dx. So again, you see what happened, that integration, of course, is like this. Again, from plus infinity to plus infinity. But this time now, I'm saying that the integration reduces to over the circle only. Why is that? So this is like magic now. They cancel each other in this case. The integration from above, I mean, this function from above and from below, because this guy is an integer, there is no log ambiguity. They both approach to the function minus x to the power n on the circle, on the line. But here, the integration in this direction is positive. In the below branch is negative. In the other direction, so they cancel each other. What remains is this integral over the circle. Because this also, I mean, yeah. Mm. Yeah. I mean, the thing is, this function really is not. I mean, the crux of the matter is that this function is a very nice function if n is an integer. There's no log, there's no branch, there's no ambiguity, minus I pi plus I pi. There's no such thing. This is just. And of course, I cannot say it's 0 because delta now is not going to 0. This is just fixed here. So how to say this? Okay, so you can just write down details of it. So that's it. So you just do the calculation here. This is not difficult using residue theorem, because you just have to identify the 1 over x part of this using residue theorem. You calculate that is equal to -1. You just show that then as zeta of -1, which is over here, you just calculate, you get that. This becomes equal to -1 to the power n times e n plus 1 over n plus 1. And this is for n bigger than or equal to 1. Yeah. So this gives a formula for zeta at negative integers in terms of Bernoulli numbers. Now, one of the things that we can conclude, okay, the first corollary. What is the first corollary? So imagine n is negative even number. So this implies, because if n is an even number, not negative even, minus n negative even number, let's assume n is an even number, then of course by facts about Bernoulli numbers, I know that Bernoulli odd Bernoullis are 0 beyond 1. So then it follows that zeta of -2k is equal to some factor. Then I've got b 2k plus 1 over 2k plus 1, but this is 0, so this becomes 0. But this already we know from other approach, but this now, at least this much we know, right? Okay, and now, what else we can say? Of course, you can say, for example, zeta of 0. I mean, this is even true for n equal to 0. Is equal to -1 to the power 0 over 1, and then if you put b1. What's b1? We can -half. So this is -half, right? So this is -half. This also, I mentioned this. I'm not sure we proved it, but it was maybe it was one of your assignment questions. E0 is equal, I mean, a zeta of 0 is -half. This follows from that. And also you can compute zeta of 1 or -1 rather. So what is zeta of? So you put n equal to 1, you get zeta of -1 is equal to -1 to the power 1, and then I've got E2 divided by 2 -1 to the power 1. What was B2 we calculated? Was it 1 over 6 or -1 over 6? Which one? Positive 1 over 6. So we get positive 1 over 6 divided by 2. So we get -1 over 12. Is that correct? Or are we off by a factor of -1? Yeah, but I'm asking because independently we know what that is. This is 1 plus 2 plus 3 plus 4. Oh, that's -112. Yeah, that's correct. Yeah, good. I thought it should be positive, but there is no logic here. No, this is okay. This is a famous YouTube thing, you know, stupid programs in YouTube. You watch, people watch, millions of people watch with amusement. Mathematicians prove something is impossible.
Extending to non-integers is not the same tricks doesn't apply, right? Because log doesn't, because the x the log doesn't simplify, right? So
Yeah.
we'll know if asked you before, we'll know probably none of them.
I doubt it. No. In this regard, I should say, I said something about gamma. I said that gamma has been calculated only for integers, positive or negative, doesn't matter, and half. But actually, there is a calculation for I also. Yeah, so that basically is I factorial. There's a YouTube, I checked it, there's a YouTube video. Actually, there are two answers that differ. One of them sounds more reliable than, one of them, I don't know, says it's 0 or something. The other one, no, says it's a real number. The other one computes an approximate complex number, actually. I mean, this is gamma of I plus 1, right? So we have a formula for it. I mean, what is the formula? This is integral 0 to infinity. What was the definition of gamma? E to the minus t, e to the I plus 1 over t dt. This is the definition. So you have to calculate this integral. Not so bad, actually. Okay, so. No, actually. Well, but I think you get algebraic numbers. I think so. I don't remember. But there are two different statements, different values. Yeah, one of them sounds more reliable. I don't know. You check it for yourself now. You just go in when you're having your dinner or lunch and you don't have any companion, you can enjoy seeing these calculations. All right. So now what happens is that, so how about zeta of 2n? How about zeta of 2n? Well, we know that, so thanks to functional equation, so what was functional equation? Again, Zs, I just write capital Zs equal to Z1 minus S, right? We know that zeta, so, and this involves zeta, right? We know that zeta of 2n must be related to zeta of 1 minus 2n, right? So zeta of 2n is related to zeta of 1 minus 2n. In other words, zeta of minus 2n minus 1. But we know what zeta of negative integers are. Is this one. So we have to replace n by 2n minus 1 in the formula, right? So okay, but they are not the same. They are related, right? What is the relation? Well, the relation is this. Of course, again, I'm just writing these things many times so that at least you. So we have pi to the power minus s over 2, gamma of s over 2, zeta of s is equal to pi to the power minus 1 minus s over 2, gamma of 1 minus s over 2, zeta of 1 minus s. Okay? So this then, so this, I'm saying this, plus the fact that zeta of minus n is equal to minus 1 to the n, en plus 1 over n plus 1 implies that zeta of 2n, by using this move, right, implies that zeta of 2n is equal to So there's a formula that I can never remember because it involves many factors. But this is equal to 2 pi to the power 2n. So pi to the power 2n minus 1 to the power n plus 1. B2n. Aha. It can be expressed in terms of Bernoulli numbers. B2n over 2 times 2n factorial. So this is the formula. So Riemann definitely could derive this, but he didn't care to write it. It was within his reach completely. I mean, but he didn't mentions this. I think he mentions only some of these other negative values. But anyhow, but this was obtained actually by Euler almost 70 years, 80, 90 years before Riemann. So this is Euler's formula. Euler obtained it around, I don't know, around 1747 or so. I mean, you know, I told you a little bit about history of Euler. So he calculated first zeta 2 and zeta 4. Then he stopped at zeta 16, but he didn't have a formula. And then he chose a different method, and he came up with this formula, which is really amazing if you think about it, because we use so much of Riemann zeta function, functional equation, relation to Bernoulli numbers of that expression, yet he calculated it with his own method, with a different method. So, so this is a good check that this is true. So, but I mean, is a general formula is as general as Bernoulli numbers are general. If you have a general formula for Bernoulli numbers, you have general zeta. Any questions or? So, okay, I promised to write the general formula for zeta of 2n, and that's at least one proof. Euler's proof, actually, it's ingenious, and it uses some hyperbolic functions and this sort of things, and complex hyperbolics, but it's not clear, actually, how he came across that proof. To me, I mean, it's just... well, this proof also is incredible because it uses many ideas. Anyhow, so question? It's all gamma functions, yeah. Everywhere you go, you meet gamma. Okay, so now I think it's good to now to look at some other instances where gamma function, where zeta function appears. Actually, I mean, one of the things you have to think about is what zeta means. Really, I mean, what is the meaning of zeta function? I mean, why this function has this magic properties? I mean, why it's so important? And you have to ask yourself, can I introduce yet another zeta function? And what can you do with those zeta functions? So you have to philosophize a little bit of like zetaology, if you want, philosophy of zeta. Yeah, it's very good to think about it when you have maybe a little bit more than usual drinks or something. Just try to philosophize about the meaning of zeta for life or for mankind or this sort of things. I mean, just indulge. I mean, it's good. It's really good. I mean, it's so one of the things I can tell you is that to many situations you can attach a zeta function. So that's at least in mathematics we know. So beyond the standard zeta function, so let me write it like this, beyond the standard zeta function, I mean the standard Riemann zeta function. There are zeta functions that attach to many, many other objects in mathematics. There are many, I really emphasize, many other types of zeta functions. Okay, I mean, it's kind of easy to say that, yeah, it's a generating function. You have some sequences of numbers and you want to gain an understanding of those, like primes or integers, and you attach a zeta and yeah, but it's not, it's too easy an answer. I don't, because we have all kinds of generating functions. Why this sort of generating function is so powerful? I don't know. I don't think anybody knows actually. Why it's just so useful and so powerful. So so the best is to look at examples. So here is one example. It's called Dedekind zeta function. For number fields. So I'm not going to assume that you know anything about number fields. So I'll just define a number field, and I will tell you how this Dedekind zeta function is defined. Definition. A number field is a field extension Q inside K, where of finite degree. I guess all of you has taken field theory, right? Or maybe Galois theory or something like that. So what does this mean? Well, Q is the field of rational numbers, right? And K is another field, but degree of K over Q is finite, right? So K over Q is less than infinite. I mean, the important thing is finite here, finite degree. So these are called function. They called function? No, number field. No. Function field is different. It's quite relevant to this story, but it comes in another. I won't talk about it. Maybe I will. I don't know. If you stay long enough, I will. So, what are some examples? Huh? What's that? Yeah, but what is the simplest possible example? Yeah, that's an example, right? What is the simplest possible example? Q, yes. K equal to Q, exactly. I mean, let's not forget the simplest examples. I mean, these are, what is wrong? I mean, they're good. I mean, K equal to Q, they're always there. Good. So degree is 1 in this case, right? Degree is equal to 1. So another example, as it was said, Q adjoint root of 2. It's called a real quadratic extension. So what is that by definition? This is the set of all A plus B root 2 such that A and B are integers. Huh? Rational, yeah, not integers. Yes. Rationals. Yes. Yeah, I mean the rationals. Yeah. I said that. Yeah. I mean the rational field of rational numbers. Right. So this is, you check that this is a field, I mean, you have to check this. Yeah, a little bit of clearing the denominator and this sort of things, a little bit of tricks, but that's okay. And what is the degree of this over Q? Of course, you know, it's 2. It's a basis of 1 and root 2, actually. Degree is really dimension of Q as a vector space, sorry, K as a vector space over Q. So dimension is 2 in this case. Now, but there is one example that was actually more or less first discovered. What was that? Q of I, the field of Gaussian Gauss rational numbers. So K equal to QI, the set of all, again, A plus IB, such that A and B are in Q. So in honor of Gauss, who studied this for the first time, they're called Gaussian rational numbers. Gaussian rational or Gaussian rationals. Okay. You can spend your life study just part of this world of all finite field extensions. It's a huge subject. It's algebraic number theory, and it's kind of parallel to analytic number theories. But there are some points of contact between the two. Okay, but I'm gonna focus on this eventually. But another definition is given a number field, K, there is a ring called ring of integers. It's ring of integers. Now, so this is a very strange definition of integer that you have never seen before, unless you have seen it. Have you seen this ring of integer definition? Yeah, this ring of integers. Huh?
Never seen it before unless you've seen it.
Unless-
Literally.
Yes, that's, but there is content there. It's not a totally void statement. There's a meaning there. Okay, so ring of integers of given a number field K, it's ring of integers denoted. Do you know its notation? Yeah, it's O sub K, right? And then the sheaf is relevant there, but let's not get into that. OK is by definition equal to the set of all, say, what is good notation? X belonging to K such that X is a solution of a monic polynomial with what? The coefficients in Z or in K? Oh gosh. Ah. I'm going to say it's Z, but I'm not 100% sure. You have to check the coefficients in Z. So in other words, because Z is in Q and Q is in K, so it makes sense to talk about that. But is it Z or K? Yeah, because if it is K, then you're saying nothing because you just clear the thing and then it's Z. Okay, great. Yeah. So in other words, we have an equation, i.e. X belongs to K and Xn plus an minus 1 xn minus 1 plus a0 equal to 0, ai belongs to Z. Okay, so this okay. So this is the picture you should have in mind is this. This is okay. This is inside K, and this is containing Q. So this is a ring. Okay, you have to check. It's not so obvious, but you check it. There are different methods of proving this. This is a ring. It's a subring of K. So what is a good examples of this? Question? Huh? Yeah. Oh, yes, Z. Oh, sorry. Yes, yes, yes. That's good. Yeah. Thank you. Yeah. Huh? No, Z. This is right now is Z. I mean, because Z satisfies this thing, because Z is in K and satisfies this condition. That's obvious. Yeah, thank you. Yeah, that's good. So here are some examples. For Q, for K equal to Q, what is OQ?
Is that?
It's Z, yeah. So you can go to your, I don't know, undergraduate calculus class and define integers for them according to this. So yeah, you check that if satisfies such an equation, then it indeed is just an integer. That's true. So another example for our favorite thing, Gaussian rationals. You can check that OQI is actually equal to Z of I. And that's not so obvious, but it's true. Z of I. But what is Z of I? Z of I is the ring of Gaussian integers now, which is of the form. So what is Z of I? This is the set of all A plus IBs, where A and B belongs to integers, right? Okay, okay, good. All right, so we have this ring of integers, which is kind of number theory in this new world of new integers, which looks much more complicated. So another example, just simple examples I'm giving really for K equal to Q, your real quadratic extension Q root 2 O K is equal to, again, in this case, is just A plus B root 2, the set of all A plus B root 2, where A and B are integers again. But things are not going to stay that this simple, I tell you. don't have high hopes. They will disappoint you if you keep hoping things are going to be so simple like these cases. Yeah.
So that Q is the fractions. That.
Yes.
What can we say about
Yeah.
the ring of integers of the field of fractions of?
The field of, well, I mean, some ring, I don't know, but in this case, I believe the field of fractions of OK is K. You can show that. So your question about extending the fact you mentioned for Q and Z, the relation, Q indeed is the field of fractions of Z, and this thing is true. So that's an extension of what you said. Question?
Try about how this O works. Like if you put O sub bracket of a ring, would that give you back the ring?
No. Well, O is, yeah, so O for me is always attached to these fields, finite extensions. I mean, in general, I don't know the O business in general. You have to think of, you have to put yourself in the setting of number fields. Yeah. Huh? Yeah, that's. I think that can be answered. But let me now move on towards my agenda. I have an agenda here. I want to define Dedekind zeta function eventually. So, okay. So now, what is Dedekind zeta function of Q of K? I mean. So definition. Let K be a number field it's Dedekind zeta function is zeta K of S is equal to sum over 1 over absolute value of I to the power S I different from 0. So let me now unpack this definition. Okay, first of all, the summation is over non-zero ideals of OK, okay? Over non-zero ideals of OK, of the ring of integers. Because we have this ring of integers, and it has some ideals. Throw away zero ideal, we don't care about that. But then the rest, there are some ideals, and we just... Now, so that's one point. The second point is, what is absolute value of I here? Is a real number. Actually, is an integer. That's the order of the quotient ring of OK by I. That's order of OK by I. So this is a quotient ring. So of course, in this definition, it's implied that if I is non-zero, this is a finite ring. And this is true. So fact is that for I different from 0, OK over I is, maybe that's what you were alluding to when you talked about, someone's mentioned FP or something, or anyhow. So OK over I is a finite ring. So you put over there. Okay, so this is a huge sum. It's summing over all non-zero ideal. S is a complex number, wants to be just general complex number. And one of the things that was Dedekind himself prove it? I believe so. Dedekind proved this. So one of the things that Dedekind proved about this is that this series is actually absolutely convergent for real part of S bigger than 1 again. So that's what he showed. So I believe this was Dedekind. Is convergent for every, so just S is a complex number again, real part of S bigger than 1. Of course, this definition, when K is equal to Q, it just gives back the Riemann zeta function. So let me convince you. for k equal to q, we get Riemann zeta function. Why? Let's see why. So we have the case k equal to q, right? Well, in that case, of course, OK is z. And what are the ideals here? Oh, we know that z is a principal ideal domain, it's a PID. So every ideal is principal. So every ideal is generated by one number, for example, unique generator, positive generator, n, right? So this is like n. N could be 0, 1, 2, so on, right? Okay, now in this case, what is z over I? Well, it's just the ring Zn. It's z mod n. And for n different from 0, I mean, for n equal to 0, you get everything, z, which is an infinite ring. But we excluded that. But otherwise, you just get a finite ring Z mod n, and it has n elements. So at least in this case, you see that it's a generalization of the Riemann zeta function, at least at this elementary level yet. Yes?
Does
Yeah.
for the ideal non-zero, okay, mod I is
I erased here. Is a fine? Didn't I write it? Huh? Is a finite ring, yeah. Maybe I said it, but I didn't write it. Thank you. Yeah, it's a finite ring. Good, good. It's a finite ring. Okay. So Dedekind was, it looks like he was on the footprints of Euler and Riemann, taking steps as they took, but in a much, much more general, kind of more complicated world of all number fields and the ring of integers. So what now? So the good thing now is to do an example and see how this can actually be computed and how does it look like for at least maybe Gaussian integers, and what are some of the properties. Certainly, they have analytic continuation, and they have functional equation, but this was not proved by Dedekind. They were proved long after Dedekind in 1920s by Eke, actually. He proved it. So I will, so maybe I think it's time to take a break because we've been going on for an hour and a half. So it's a good time to take a break, and then we come back in 10 minutes. We'll have class for 10 minutes again, and then we'll say goodbye. Or I can continue if you want, and then we'll finish maybe quarter to. Is that okay? I can continue for 15 more minutes. Is that okay? Because we're going to be kicked out at 3 anyhow, so we better save up. Really? Why? Oh, really? Was it always like that? Hmm. I see. So I can keep going then. You're suggesting? Okay. Right. Now let's look at the case of so first of all, by the way, any questions about the logic of this? I mean, at this stage, looks like it's just emulation of Riemann's zeta function. Just formally, we just repeat. Of course, there are some steps that are not trivial, like you have to see why this is finite. Okay, you do in algebraic number theory. I mean, this was known to Dedekind definitely, and then or why this is convergent for real part of S bigger than 1. That's another issue. But yeah. But any question? Yeah.
What if, guessing some,
Yeah. It tells you about the structure of primes in this number
in the
field.
number field.
Yeah.
Oh,
In the ring of integers of the number field. Yeah.
okay.
But primes are, the definition is different. So I will, so actually, I'm glad you mentioned that, because before I go do the calculation now, let me write down one of the big facts about these ring of integers OKs that was proved by Dedekind actually, and then we'll see what we can do with that. Yeah. Yeah, that's that was a very good question. Right. So now, so we need a definition of prime ideal. So an ideal P inside OK. I mean, this is for any ring, actually. You don't have to be in OK, but I just want to work with OK. Today, I really love OK. I don't want to get out of OK. So you have OK. An ideal P is called prime. If xy belonging to P implies that either x belongs to P or y belongs to P. Is that everything? Huh? And P should be, means what? And can be 0? It can be?
Your ideal prime.
Oh, for integral domains, that's okay. Yeah. Yeah, for integral. So, yeah. So, and so let me at least put it like this. And P should be different from OK itself. Because, I mean, certainly for the big ring, it's true that XY belongs. About 0, I think, yeah, we don't exclude 0. Because for integral domain, 0 is a prime ideal, in fact, in that case. Okay. So this is prime ideal. Now, there is a theorem due to Dedekind. This is called, again, unique prime decomposition. Oh. So they're coming already?
No, I think you said it wrong.
Oh my God. Unique prime decomposition. For any ideal I inside pk, so I mean any ideal I inside OK can be uniquely decomposed. Well, uniquely means essentially uniquely up to permutations and trivial modifications of the product in different orders can be uniquely decomposed into prime ideals. I mean, I say I can be written as P1, E1, E2, E2, PK, EK. These are distinct prime ideals, and these are some powers. And the only thing that you may not know here is the definition of products of ideals. But you know that, right? Definition of products. Okay, so this is the one. Okay. So this was a big theorem that was proved by Dedekind. Now, using this, I can write this Euler factors or the Euler product formula now. So using this, so the emphasis is on uniqueness and primeness here. So then a corollary is Euler product formula for it's so funny. It's just so funny.
It's so much confidence.
Yeah, you came all the way in.
Yeah, no. There's something funny about this whole thing. Euler product formula for Dedekind zeta function. I don't know for Dedekind zeta function. So zeta k of s, which was originally defined as 1 over absolute value of I to the s, I different from 0, can be also written as sum 1 minus 1 over absolute value of p to the s inverse p prime. Oh, gosh, yes, of course. Yeah, it means we have to go now, yeah. Product, yeah, of course, over p prime. I mean, isn't that a grand generalization of Riemann's or Euler's product formula? That's so in general now in this much bigger, much more general context, we have this thing. And the proof is exactly this. And you just follow the proof in the case of thing, and then you have that. Right. Okay. So what we're going to do now. So let me write these two facts that was proved about them, and then I'll tell you what we're going to do, because we have to do some very non-trivial calculation here. So I will tell you what we will do. So first of all, let me write the facts. Fact is that zeta k of s has an analytic continuation to I believe complex numbers minus 1 again, although I'm not 100% sure. I have to check to c minus 1. So this, check it for yourself. That's important. And satisfies functional equation. Really, really, this is just mimicking behavior of the Euler-Riemann zeta function, and satisfies a functional equation. I won't tell you what the functional equation is, though, because it's complicated, more complicated than the Riemann functional equation, and satisfies a functional equation.
It's okay.
Huh? Its form, no, I mean, it's form very general. I think it's related, just again, relating zeta k s to zeta k1 minus s, but those factors are different. There's some fact. Yeah.
I don't really.
You mean this one?
Yeah, so I think we want to say non-zero.
Yeah, no, in this case at least.
And factorization.
Yeah. Oh yeah, you're like me, one of those people always worried about zero. Yeah, really. Zero gives me nervousness. Nice, yes. So you're saying if I is 0, what happens? We cannot. What are you saying?
Well, I guess it's strictly true of -0, but
Yeah.
I think you want to say non-zero.
But I mean, I have in this case a general idea.
Zero or
If you put zero in, then you get zeros. You don't get non-zero ideal by multiplying by zero ideal.
but I is
Yeah, because you have to take sums of products of all those elements, and each product contains a zero, so it becomes zero sums of zero.
but these factors,
Yeah.
I is zero,
Mm-hmm.
and then is zero. E could not.
Oh, that's not unique. Oh, yeah. Okay, so those trivial cases you handle yourself. Life is too short for me to worry about those things. Yes. Yeah, no. That's a good point. Yes. I mean, okay. So, but we know what we mean by this, really. I mean, just yeah. I mean, when I think about rings, I always think about zero ring. I don't know why. What happens in the case of zero ring? That really makes me nervous. Yes.
So is there a Riemann hypothesis or look?
Yes, there is Riemann hypothesis for these things. Obviously not proved. It's going to be as difficult as, if not more, of the original Riemann hypothesis and this thing. So this was proved by Hecke first. I believe around 1920, Erich Hecke. Or not 28. I mean, this is 2020. Yeah. Amazingly, he used the ideas of theta functions. He mimicked Riemann's proof, basically, but in a much more elaborate way. So he had to introduce new types of theta functions, modularity property of theta functions, and those things. Eventually proved it. I mean, the proof was more or less within the reach of Dedekind. I don't know why Dedekind didn't prove. Yes. Yeah.
So
Yes. They come into the picture. In fact, in the example, we'll see. Yeah, exactly. Yes. So anyhow, so I think this is another piece of zeta philosophy I want you to have in mind. But it's a good idea to think about zeta function all the time. So when you check, see if you can define zeta function for rings, zeta function for groups, zeta functions for dynamical systems, zeta functions for this, for that. Maybe you will introduce your own zeta function, and then zeta function for manifolds, which is a spectral zeta function, is much more complicated than these things, of course. So they are all. Yeah. So what I'm going to do then, I will study this zeta function for the special case of K equal to ring of Gaussian, K field of Gaussian numbers, rationals. And then we will compute it exactly, and we will check one statement, which is the class number formula in terms of residue of this zeta function at s equal to 1. This residue contains a lot of information about the number field, actually. Maybe that's the question you ask also. So we will see that in general, residue of zeta ks at s equal to 1, it contains lots of information about the number field. It has there's a formula called the analytic class number formula, which contains contains the regulator, contains the class number, contains the discriminant, contains the number of real and complex embeddings, a lot of things is packed. So yeah. I think this we will do on Thursday. Any questions? Maybe I'll just close the thing, then